All right, so this is going, respond to the attendance poll. Again, option D for attendance, okay? And it's, again, just for you. Okay, so today we are still talking about generating random variables. And so far we've covered a bunch of methods, primarily inverse CDF, rejection sampling, and then, wait, so what do we do? Okay, we did inverse CDF, we did rejection sampling, we did some transformation or composition methods, okay? So that includes the Box-Mueller transform and these, convolutions using kind of the definitions of random variables, okay? And so now we are, I will say, we're at a place where we have our UNIF and basically our norm, okay? Via some kind of transformation method, we might be able to do our norm. And so far we're able to generate, for most distributions, pretty much, we can generate random samples from that distribution, if we do a little bit of thinking. But all of our distributions so far have been one-dimensional, okay? Have been unit distributions of one variable. And so today we're going to take a look at generating values from multivariate distributions, okay? So, all right, so let me just write this. Okay, so far, we covered methods to generate values of random variables. Okay, so we've got inverse CDF, we have rejection sampling, we have some transformations and convolutions, okay? Okay. But these have all been, so far, univariate, okay? When's our first midterm?
Next Monday.
What's that?
Next Monday.
Fourth week Monday, right?
Yeah.
Okay, all right. So, thinking of questions and problems, just make sure you know all of your kind of these methods, and then I'll post up a homework, okay? Probably today that covers stuff. All right, you'll see, okay? All right, but today we will look at kind of multivariate distributions, okay? Specifically, today we will look at generating values multivariate distribution, okay? And this is all covered in our textbook, okay? The Robert and Casella Introducing Monte Carlo Methods textbook, and you guys all have it, right? Because you're able to download it for free, and then it was assigned as part of your reading, so make sure you do your reading. This is covered in there, but in the textbook they only give like 2 paragraphs to this topic, and so I'll expand on it a little bit more for us. Okay, so specifically, we want to generate values from let's say, a bivariate normal distribution. Okay, so let's say generating values from a bivariate normal. Is this also covered in 100B? No? Yes. Maybe. Okay, well, so for a bivariate normal, what do we have? We're going to generate variables x1 and x2. x1 and x2 come from the normal distribution. We might put a little subscript 2 here to indicate this is a two-dimensional normal. Okay, and the normal distribution has mean mu, except it's a vector because there's a mean for the x1 coordinate and a mean for the x2 coordinate, and then the we have a sigma matrix. Okay, so mu is a vector for mu1 and mu2, and then sigma is a matrix consisting of basically variance 1 squared and variance 2 squared. So this, and then what do we put in the diagonals? The covariance, right? And just where this is the covariance of your random variables x1 and x2, which is equal by definition to the expectation of x1 minus mu1 times x2 minus mu2. It's just a definition of the covariance right there. Okay, so you've got the variance of x1 and the variance of x2, and then in the off diagonals you have the covariance. And if the covariance is 0, that means what? X1 and x2 are independent, right? And if they're independent, then you might as well you can sample x1 from one normal and x2 from another normal independently, and that's fine, okay? So if equals 0, then x1 is independent of x2, and we can just do x1 comes from normal with mean mu1 and sigma 1 squared, and x2 comes from normal, mean mu2 and sigma 2 squared. And then if we were to plot that, what would the contour plots look like if we put on x1 and x2? If they're independent, you would get, your contour plot might be a bunch of ellipses, but those ellipses will be, is concentric the right word? I'm sorry, they're going to be concentric, but the axes will be perpendicular to each other. Okay. But on the other hand, if sigma 1, 2 is not equal to 0, then you have some covariance. Covariance exists. And this means that, as x1 tends to be greater or smaller, then x2 will also be greater or smaller depending on the values of the covariance. So you might have something that looks more like this as far as your ellipses go. Okay. So here, sigma 1, 2 would be greater than 0. Okay, and so the question is, if we're able to do this, if we can get x1 and x2 normal, okay, can we somehow get something with covariance, right? So all right, so to kind of simplify things, I'm going to just start off with sampling from the standard normal, okay? So we'll say, so based on our previous work in the class, we are now at a point where we can sample standard normal variables, okay? So we can, sorry. So we can now sample Z1 from normal 0, 1, and Z2 also from normal 0, 1, okay? And what we want is to somehow get values x, okay? We want values of x, okay, that will have x1 and x2 coming from normal with mean vector mu and covariance matrix sigma. Okay. So we'll combine. So we combine Z1 and Z2 to get just Z. And we will just say, so Z is equal to just Z1 and Z2. And these will come from the normal distribution, two-dimensional normal distribution with mean vector 0 and identity matrix as our covariance matrix, right? So our 0 vector is just 0, 0, and then so if we do that, this is what we have right now, okay? And so what we want to do is we will try to find, we want to find vectors B, matrix A and vector B matrix A and vector B, so that X can be defined as our B vector plus our A matrix times Z, and that this thing will then come from the desired distribution. Okay. All right. Is this possible? Yes. Okay. We can do this. Okay. So we're going to search for some vector B and some matrix A, so that when we multiply A times Z, where Z is just coming from basically two normal, standard normal distributions, we can do this, okay? All right, so all right, let's say, okay, so our vector u, the mean vector u of the can be defined as the expectation of the random variable x. Okay. Okay, so u sub x is expectation of random variable x. Okay. All right, just so you know, I've got an attendance poll going, and I'm going to close it in like 2 minutes here. I'm like super generous with the late. Okay, so at 9:20, I'm going to close the attendance poll. So if you're here, make sure you respond to that. Okay. All right, and then we're going to define. We define x as b plus a times z. So this is going to be the expectation of b plus a times z. Okay, and b is just a constant. So the expectation of b is just b plus, and then now we have to get the expectation. Z is the only thing that's a random variable, right? So, you know, b is a constant. Z is a random variable. And then we can pull out a, because a is just a matrix, but it's a constant. So this is going to be a times the expectation of z. And the expectation of z, so z comes from normal 0 and an identity matrix. So the expectation of z is going to be the 0 vector. So this just becomes b. Okay, and so so we can use so we can set b equal to mu. All right, mu being mu the desired mean. Huh? No. So we have. So this is. Sorry. Maybe I used x too many times here. But we're going to say x is b plus a times z, and we're going to say, okay, what's the expectation of this thing? The expectation of this thing ends up to be b, and so if we desire to have a different x variable with this mean mu, we would set b equal to this thing, and that will ensure that the mean of this variable x defined this way will have this mean vector.
So that mu vector is a mean vector for x.
It ends up that way, right? So okay, so our goal, I probably should have used a different letter here, okay? But our goal is to have some variable that has mean vector mu, okay? And what we're saying is we're going to define this variable x as a vector b plus the matrix A times some independent standard normal values, okay? And we're going to say we want the expectation of this x variable to have the expectation of this, to have this mean vector. And we found the expectation of this thing is just b. So we can set b equal to what we desire. Is that okay? All right, now we want to find how are we going to get the matrix A so that the variance covariance matrix of this variable x will equal what we desire, right? Okay, so how can we find matrix A so that the covariance of x, which is defined as b plus a times z, will equal the desired covariance matrix sigma. Okay, so what we're first going to do is we're going to find out what the covariance of x is in the first place, and then we will set that thing equal to this. Okay, so let's find what the covariance of x, okay, is if x is defined as b plus a times z. All right, so the covariance of x is equal to this, all right? And so this will be the covariance of b plus our a times z. Okay, so b being a constant has no influence on the covariance, right? So this just becomes a times z, right? So b is a constant. That's just added. So there's no covariance there. It doesn't affect the covariance. Okay. How can you pull out the a from a covariance? So if it's univariate, you pull it out and it becomes kind of a squared, right? But because we're dealing with matrices, what this becomes is you pull out the a in the front, and then and you have another a afterwards, okay? And this is how we get it, okay? So we have a covariance a transpose. Okay, and we know that the covariance of z is equal to what? The identity matrix, okay? So we have a transpose, and this just becomes a transpose, right? So sigma, the covariance of x is equal to a transpose. All right, I'm going to go ahead and close our poll here. Okay. All right. So what we want now is, so we need to find a so that a transpose will equal the desired sigma. Okay. Do you guys know, do you remember how this can be done from your linear algebra class? Well, All right. Do these terms mean anything? Okay. So we'll say we have some matrix sigma. We have a matrix sigma that is symmetric and positive definite. Right? Matrix sigma that is symmetric and positive definite. Okay, and that means well, positive definite means the eigenvalues are all positive, but that means there exists a lower triangular matrix A such that sigma equals A transpose. Okay, and this thing is called the Cholesky decomposition. Does that sound familiar? Okay. All right. So how do we do the Cholesky decomposition? Okay, so we're going to say A is lower triangular. So that means we're going to define A as equal to this T11, T21, and T22. Okay, and then so that means AA transpose will equal T11, T21, T22 times the transpose of this, so T11, and then this flips around. Okay, and we want to set this thing equal to sigma 1 squared, sigma 1, 2, sigma 1, 2, sigma 2 squared. Okay, can this be done? Yeah, you'll get, all you have to do is, you just have to do a little bit of algebra. Do you want me to do this, or do you want me to just go to the answer? Yeah, let's do this, okay? Let's not be lazy. All right. Huh? Algebra can be hard, right? Okay, so let me just, sorry, I got to recopy that. Okay, so I got T11, T21, 0, T22. I didn't do the algebra in my notes, so if I make a mistake, please correct me. Okay, so if I multiply this out, so let's just do the matrix multiplication. So this is T11 times T11, so I get T11 squared plus 0 and 0, okay? And then in the next term, I will have T11 times T21, and this gets multiplied to 0. And then over here, I have T21 times T11 plus 0. And then lastly, I will have T21 squared plus T22 squared, yeah? And this is equal to sigma 1 squared, sigma 1, 2, sigma 1, 2, sigma 2 squared. Okay, I have basically 4 equations and 3 unknowns, but 2 equations are identical, so So I got T11 squared is equal to sigma 1 squared. And then we've got T11, T21 equal to sigma 1, 2. And T21 squared plus T22 squared is equal to sigma 2 squared. Okay, so this gives me that T1 is equal to this root of sigma 1 squared, or just sigma 1, okay? And then, and if I have that, then this becomes sigma 1 times T21 is equal to sigma 1, 2. So, so that turns into T21 is going to be equal to sigma 1, 2 divided by sigma 1. Okay? And then if I plug that in now, then I have sigma 1, 2 divided by sigma 1 quantity squared plus T22 squared is equal to sigma 2 squared. And then, so rearranging terms, T22 is going to equal the square root of sigma 2 squared minus sigma 1, 2 over sigma 1 squared. All right. Yeah, question?
Is this possible for A to be positive semi-definite?
Positive semi-definite. So I think if it's positive sorry.
If B is not zero,
I got to think about this. I think if we look at the Wikipedia page on Cholesky decomposition, it says it will exist if it's positive definite, but if it's positive semi-definite, I think you can run into some singularity issues. But I got to think. All right, sorry. Okay, so anyway, we've got these values now. Okay, so now we have A. So all of this comes together. So will this fit on your screen? So now we can define our matrix A as being sigma 1, 0, and then sigma 1, 2 over sigma 1, and then this, now I have to fit this whole thing here. Sigma 2 squared minus sigma 1, 2 over sigma 1 quantity squared. Okay, sorry, I know that doesn't fit on the projection, but I'm just plugging in the values T1, T21, and T22 into our triangular matrix A. AA transpose is equal to that. All right, is that okay? So now that we have this, okay, so we can have, so if, so we define X equal to our B vector plus A times Z, okay? Z is equal to Z1, Z2, and these are coming from normal, I guess a bivariate standard normal. B is going to be defined as mu1 and mu2, and A is going to be defined as the matrix. I forget what I just wrote, but T11, T21, 0, and T22. 2, 1, 2, 2, 2. Okay, and then so x defined this way will come from a bivariate normal. All right, is that okay? So now we are now in a position to generate values from some kind of bivariate normal density, and so let's just do a little quick demo here. Okay. So I think it's not too hard. Like if I give you an easy example, it's not hard to get the Cholesky decomposition, but we can have R do it for us very quickly. Also, here, I already did it right here, but okay, so let's say, here, I'll set a seed. Let's say I want to generate 500 points from, let me resize this so it fits. Okay, so let's say we want the mean vector mu to be, I don't know, we want a mean of 3 and a mean of 4. Okay, these will be our coordinates, and we can create a sigma matrix of the vector. We'll do 1, 0.7, 0.71. and rho equals 2. Okay, so that's what mu looks like, and this is what sigma looks like. Okay. All right, and so what we want to do is we're going to get z, and these will just be independent normal. Okay, so here I'm going to basically do our norm, but into a matrix. Okay, so here, what I can do is I can just do C bind, and I can ask for our norm n and our norm n. I think that'll do it. Okay, so basically I'm asking for a vector of standard random normals, and I'm not C bind. I want an R bind. Sorry. Okay. And if I ask for the dimensions of z, this will give me 2 rows, 500 columns. Okay. All right. We can ask for the Cholesky decomposition of sigma, or we can find this ourselves. Okay. So I can just ask, what's the Cholesky decomposition of sigma? And this gives me the kind of the upper triangular matrix, but so I can just say A is equal to the transpose of the Cholesky decomposition of sigma. Okay, and indeed, if I ask for what is A times A transpose, then I get back our sigma matrix. Let me just plot z for you right now. Okay, so this is standard independent normal here. Let me do aspect ratio 1, PCH equals 19, and I'm going to make our points a little bit smaller. Okay, so this is what we have right now. If I've got this sigma matrix, what should our plot look like? It should look like, I don't know, got squished and skewed a little bit, right? So we're going to define x as equal to our mu vector plus our a, which is the Cholesky decomposition, times z. Okay? And that's that. Okay? And then let's ask for the dimensions of x. 2 by 500. Okay. Let me plot the transpose of x. Just copy this actually. Okay, and there you go. And so now we have a bivariate normal. Okay, we can ask for what is the variance of z? Oops, I gotta do transpose of z. Okay, so when we ask for the variance of z, we're getting something that's close to the identity matrix, but because it's a random sample, it's not exactly so. Okay, so we get 1, something close to 0, and something close to 1. And then if I ask for the variance of x, I gotta do transpose of x, we get 1 and something close to our desired sigma matrix. Okay. All right. Okay. Are there any questions on this? Yes. Yeah, you know, because the way we defined it in our math is we said we kind of defined our each increment of x like this, and then so what our when we have this, it ends up going to be like x1 value 1, x1 value 2, x1 value 3, and we're going to get basically x1 and x2 value 1, x2, something like this, all the way up to x2, 2. Now, what R expects, R is expecting x to look more like this. So I'm transposing it that way. Okay. Any other questions on this topic? Okay. You should be able to do a Cholesky decomposition by hand for a covariance matrix. I mean, we did the algebra here, and so it shouldn't be too terrible. And then you'll have an exercise to try this out. We can also add contour plots to all of this, and so in your homework exercise, I believe I asked you guys to do that. Okay, and I'll reference a link on Stack Exchange where they show you how to do that. Okay, we'll end here for today. Have a great weekend, and we'll see you guys on Monday.